Okay, hope you had a nice lunch, and please welcome Lars from Scling to talk about securing our software supply chains.
Thank you. Thank you all for coming. You're one of the few people that pronounce the company name correctly. I'm Lars. I'll tell you about what the company does a few slides in, so I'll skip that part. I usually talk about data. Today's topic is the software supply chain and security in the software supply chain. I listened to a keynote by Vint Cerf the other day, and he summarized the situation of security as a battle that we're losing. And unfortunately, there are other, even more important battles that we're also losing. One of them being the climate, which you are very well aware of, and this is what graphs of losing battles look like. And the other one is, unfortunately, democracy. It has overall in the world improved since World War II, but for like 15 years ago, it started going down again on a summarized basis, and that's slides on the graphs on the left. I believe that these are interconnected. In order to solve the climate changes, we need to live and work smarter. We need to put more software into our things so that they can be more resourceful with the carbon dioxide and so forth. And we need to prevent rogue actors from manipulating our elections. So I think that we have a job to do in terms of IT security in order to take on these challenges and turn the tide. I've sort of, as a tech nerd, I feel a responsibility here because technology is sort of driving progress in the world. And if I look back and what have we contributed in the past in these battles, we have contributed good things like the internet, which has spread information in the world and so forth. But there are also a couple of things that we have contributed that are holding us back or that are contributing on the wrong side. One of them being surveillance capitalism, which we sort of invented because we thought it was good, but it had a massive side effect that we have now established a way to measure and manipulate populations at scale, which affect our elections. And we have also invented new ways of monetizing bad security in the world. It used to be the case that if you were able to breach someone, which you have been for ages because security has always been so-so, then the most lucrative thing you could do was to send spam, which isn't all that lucrative. But nowadays we don't need that because we can turn the CPU cycles into pure money because we've invented cryptocurrencies. And the same invention has also enabled ransomware. You couldn't really charge for even if you took somebody ransom before. So we have created this fantastic tool for the criminals. And since we can't seem to get our act together and take that invention back, we need to fix security instead in order to turn these tides. How do we do that? I don't have a solution for everything, but I think there is a simple solution to fix application security, which is a large part of the security problem or of the security challenge. Traditionally, the way that we work with application security is that we have some people building features and applications and things that we can sell, and then we have some other people that have a contradictory goal, like to keep these other people back so that they don't increase the risk of the company or the technical operational risk. And when you pin these people against each other, risk management rarely wins. In the same way as in the casino, the house always wins. Like the features and the revenue generation always wins. So we keep on having this trade-off and we keep deprioritizing the risk management where there's security over other types of risk. I believe that the simple solution is to align these things and do things more things that are that also both improve security and improve productivity. And we have lots of these things. We have things that don't on the right, like pen test and phishing campaigns and blah, 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 all the things that we do that take time from our feature development. But then we have invented a bunch of things that make life easier for us and improve security, like single sign-on or keeping passwords in password managers and so on and so forth. So I believe that the simple solution in order to make significant progress is to do more of the things on the left and less of the things on the right. And for the things on the right, where we don't currently have a good solution that is also improving productivity, we need to invent those solutions. And we need to align people so that you put people together that have the same goals. This solution is simple in the sense that I can describe it here, but it's not easy. Right? It's simple in the same way as losing weight is simple. You just eat less and exercise more and done, but it's not easy. I believe that it can be done because we have come up with a similar solution before. I'm old enough to have run like Windows 3 and things like that on my first computers. And the most important feature of Microsoft Word was the autosave feature because it would crash all the time. So you needed to have things saved so that you could get through and write in your document. This is from Windows 95 and 98. For 7 years, it remained undiscovered that a Windows computer, if you just have it sitting there for 50 days, would automatically crash. You would think that like some classroom somewhere, they leave the computers on and some sysadmin would come and say, who? After 50 days, all of them crashed at the same time and noticed. But no, the expectations were so terribly low on the quality of software at the time that nobody noticed for 7 years. Nowadays, we still think that software is terrible and don't do the things that we hope to because that's human nature. But we have massively more complex systems. And whenever they slightly misbehave, as in the example here, like your email notification service over-delivered just slightly, you hadn't tuned it properly. I'm so annoyed that this is worth tweeting. The expectations are up here when it comes to software these days because we have fixed quality. How did we do that? We found ways to align productivity with quality so that the things that we do all here improve both of these things. And all of these things are examples of getting people from different disciplines to work together and align their goals and say, you people now have the same goal. Why does this happen? Another way of looking at it is that we have industrialized software engineering. The things that we do as humans to create value, first in history, they start out like with manual things, with handheld tools, without machines in them. So if we want to chop down a tree, we take an axe or a saw and go out in the wood and chop down a tree. And then it evolves as technology evolves. So we get tools to hold in our hands that have machines and power in them, and we have a chainsaw and can chop down a tree. And then it becomes industrialized, and we have a whole, not only sort of industrial robots and similar machines, but also a whole chain of activities. And whenever we are out here in the industrial stage, when we improve things, we don't really improve the machines so much, we improve more of the processes. So McDonald's is not more efficient than your local restaurant because they have better tools to use. They are more efficient because they have slimmed the process. And you might like your local restaurant better than McDonald's, but if out on the industrial side here, you cannot, if you're on the left, you cannot compete with the industrial side, neither on economy, efficiency, nor quality in terms of like, if you define quality as lack of defects, for example, hygiene in food. So what has happened with the software engineering industry is that we have managed to industrialize it. It used to be the case that we would build software by going to the designated build machine and type in commands, and we would get a CD or a DVD, and we would do sort of the manual build step or the power tool build step. We don't do that anymore. Like, we build VM images and we build containers. And we've turned it into a process that builds from a blueprint, builds discardable artifacts that we don't mutate. We do the same for infrastructure in the cloud and so forth. And if I were to say to you that, okay, you build this container by taking your container that you have and you exec into it and you run a bunch of commands and then you save it, you would be calling me nuts. Of course, we work to improve the process in order to change our containers. We haven't arrived there with security. We've started scratching on this process by the thing that's called DevSecOps, which is essentially industrialization of security, but we aren't there yet. But I believe that we can do this journey. What happens when you go into this sort of industrialized phase is that the quality versus speed is no longer a trade-off. If you build things with your hands or with your power tools and you are done with the artifact, you have a choice whether to improve the quality by working more or letting it go and sort of gain speed but sacrificing quality. But when you get to the industrial stage, it's no longer a trade-off. Whatever you do to improve quality in the process improves also speed and the other way around. We've seen this in the manufacturing industry where Toyota is the leader. I remember reading the book, the Toyota Production System long ago, and which was a revelation that was baffling to me. One of the things I remember from back in the 90s, if you looked at vehicles, and the margin per vehicle on the price sold, the profit, if you look at that ranking, Toyota Corolla was in the top, a very cheap car, and Mercedes and BMW at the time were in the bottom. Expensive cars, but way, way more expensive to build. The Dora research produced the State of DevOps report when the first one came out for now a number of years ago. And they concluded the same, that it's no longer a trade-off between operational resilience and operational quality and speed of delivery. So that the companies who were shipping the fastest to production also had the best resilience and quality in production. And I was so grateful for this report because it cut down or shut off a lot of discussions I've had with clients when they say, oh, we can't do that here because ... And we can say, no, sorry, you are on the wrong track here. So, I tried to write my presentations around 3 themes because those are the things that I want to see in presentations. One is the first theme is, okay, I observe these patterns based on things that we've done before. In this case, I'm not a security person primarily, but I have seen this quality versus speed change from the inside. I used to work in Google with engineering productivity, and I've also helped sort of Spotify become more industrialized in these things. And I believe that we can apply the same principle, the same transformation to security as well. I stood on a stage at Jfokus 4 years ago, speaking about how to technically solve some of the GDPR requirements in big data context. That was the spring of GDPR. And I was a freelancer, and I'd seen a couple of those implementations, so I could speak about it. But most companies were terrified to speak on this subject because they didn't want to tell people what they were doing. And so I was the only one speaking on this particular subject, GDPR in big data context. Not the only one at Jfokus, but the only one globally. I haven't found a single person who did that before the GDPR came into effect. And I believe that that's not sufficient when it comes to addressing the security problems. We need to share what we do with each other so that we can all learn, because we are not competitors here. Our competitor are the non-democratic countries who want to undermine our democracy. So I'm going to show you some things. One, how we work, and two, a thing that we did, which is at least mildly innovative, and sort of how it worked out. In order to show you how we work and why we have sort of made the decisions that we made, I need to speak a bit about what it is that we're selling, what it is that our product is. And I absolutely hate product demonstrations on stage, so I will keep that to a minimum, but I need to describe the context, so bear with me. So what we do is that we sort of do industrialized data processing. We have taken the same principles and applied that to sort of data processing, and we sort of sell that as a service. We've seen the same journey with industrialization in data as we have with software engineering, except that we're 1 to 2 decades behind here. So from the sort of power tool stage of microservices and most of the data processing in a data warehouse, what happened during the big data hype was that the most technical companies enabled by Hadoop managed to go into an industrial stage where you work with the processes rather than with power tools. We've seen a bit of dance here because the big enterprises, they failed to adopt these work methods. They adopted the technology, but they didn't adapt how they work with it, so it didn't really give them all that much. And we've now seen a sort of a lashback back to what's called the modern data stack, which is essentially better power tools, but the traditional ways of working. We saw the same with software engineering, where low-code tools started popping up, and we had 4GL and UML tools. And you see on the left here, we have rational rows. On the right, we have Apache NiFi, which is a popular low-code data tool, and they sort of look sort of the same. In software engineering, we solve these by educating more software engineers so that we can dump these tools, because you cannot build an industrial software engineering delivery on these. So I think that's what's going to happen with data as well. So we do this on the right, the industrial stuff, which corresponds to how data leaders work in the world. They all sort of adapted these things, and they have the centralized data platform where they take all of the data, they refine it, and they spit out refined data out of that platform and back into the services or for reports or machine learning models and so forth. And if you look at the numbers, in the same way as Dora research concluded that the span of measurements in terms of resilience is about a factor of 1,000 between the best and the worst in class. If you look at your typical conservative enterprise and their data, business intelligence departments or their data departments, they produce on the order of 500 or maybe in the low thousands of data sets on a daily basis, where a data set can be a report or a recommendation index or whatever. If you look at Spotify, they count their number of data sets daily on by the hundreds of thousands, probably up in a million right now. Google is counting their data sets produced on a daily basis by the billions. We're not there yet in Sweden. So we sort of replicate this way of working and offer that to our clients. And what we have managed to do that most companies have not is to sort of replicate the efficiency. So if you count number of data sets per employee, we're at the same levels at Spotify approximately. So why does this matter? It matters because we are selling productivity with data. That's our sort of the product that we ship and sell to customers. And this is crucial. If we undermine that productivity, for example, by doing too much security that does not improve productivity, we are out of business. So, and we need this speed to be able to work with client data, because if it was our own data, we would know the data, but we don't know the client data, and it turns out that the clients don't know the data either. So we need to sort of pivot and experiment our way forward. And we need to always keep the operational overhead at an absolute minimum, so that we can, per person, per employee that we have, manage pipelines that produce hundreds or thousands of data sets on a daily basis. So and this cannot be compromised. We also, of course, have the constraint mentioned in the title. We have very little money. We are a bootstrap We don't have any venture capital. So all of the little runway that we have is based on our previous revenue. Given these constraints, this is what we've sort of come up with as a general security strategy. We're happy to invest in things, but only if it also improves our productivity. And these are a number of examples. We have our online services are hidden behind the Google single sign-on, for example. A great way to get fairly high security without, and it makes life easier for us, so forth. I will zoom in on a couple of these things, patch management and the encoding processes in code, and also minimizing the attack surface. Since we're very small, we have to take advantage and do well in security that is easy to do for a small company, such as minimizing the attack surface and having a strict asset management, because we cannot afford the things that only make sense for larger companies, like very excessive monitoring, for example. So, we aim to minimize our attack surfaces in a number of dimensions. We have try to keep the number of ecosystems that we have very small. And you see them up there. We use Scala for the business logic and Python for everything else, basically. And we keep the number of components small, and also we keep the number of versions for each component small. So that when a thing like log4shell comes along, and we ask ourselves, do we use these versions that are vulnerable? It took me about a minute to answer that because it was only defined in one place. We don't have a direct dependency on log4j, we have a transitive dependency on log4j, so it wasn't clear. Now, keeping the number of versions small is difficult. Most companies don't do that. They rather have autonomous cells where each team can have their own dependency journey, so as to avoid dependency hell. So if you want to do that, you have to actually control the journey that you have through dependency hell in order to make this reasonable. So we apply the same basic principle as Google does. They also have a single version for each third-party component. I'll get to that more in a minute. This is the sort of the list of our full software supply chain. Besides cloud and VMs and container images and so forth, there's of course JVM dependencies, which we suck down from Maven Central, just like everybody else, Python from PyPy and so forth. There's what I call direct downloads here, which is essentially curl a tarball, verify the checksum, and unpack it. We use Bazel for build. I'll get to that more in a moment, but the plugins work similar to the direct downloads. You have a version and a checksum, and you download, and you verify them as they are downloaded. So for each dependency that we have a choice how we specify the version. We can specify exact versions, which is good in terms of application stability because we know that they don't change. We can specify range, which is common in Python environments, at least with Python transitive dependencies. They usually say at least 7.1, but less than 8.0. In JVM world, it looks like an exact version, but it's actually an open range, at least this version in practice, at least with the tools that we're using. Or we can simply say, we don't care. We take whatever is latest, which means that we get patch vulnerability fixes and so forth quickly. The choice to make depends on how much we trust the provider. So in cases of, for example, Google and Canonical, they seem quite trustworthy, so we are happy in many cases to take just the latest and trust that they do something reasonable. There is also trade-offs when it comes to upgrading, right? If you upgrade very aggressively, very quickly, potentially on every build, then you get vulnerability fixes quick, but you open yourself to, for example, rogue code or instability in your application. Whereas if you are very conservative, then you have a long latency until you get these crucial patches to the vulnerabilities that have been discovered. So we scratched our heads and we decided that we were to aim for exact version specifications, but to automatically upgrade those versions, to sort of try to get the best of different worlds here. And in order to minimize the risk of application stability and also vulnerability or rogue code, we also lock down the transitive dependencies. So the sort of rest of the presentation is sort of how to pursue that goal. And I've lost a bit of time here, so I'll try to speed up. So we try to be up to date, but the up to date has different definitions. There are a number of different scenarios that can happen. One is that there is no new version of dependency A. Good, we are up to date. There's also the case that there is a new version, and that if we upgrade our application still works. Great, we should do the upgrade. And then there are various other scenarios, like there exists a version, but it will break our application. There exists a version, but it will break our under dependency B, which depends on that, and there might or might not be a new version of B that fixes that, and so forth. So this is what sort of dependency hell is all about, sort of navigating that mess. And if you try to upgrade something, you get this entangle of other things that you need to upgrade first, which is a terrible task as a human to go through, but it's very friendly for a bot to do. Because whenever you try something, you need to run the test suite, and the test suite takes like minutes. So you lose your productivity as a human, but a bot has more patience and can do this and try its way forward. So that's the approach that we took. There are bots out there. They were not near doing the work that we needed, so we sort of discarded them. One is that they're way too complex for the task at hand, and much of the complexity is to figure out whether there's a new dependency, which it turns out is a problem that doesn't really need to be solved. They also don't really care about whether my application is correct or not, as far as I can tell. I'm sure it's possible to hack them to do that, but I couldn't find an easy way to do that. So running a bot only works if you have a strong process. By strong process, I mean that if we do a change and it breaks the application, we have a means to detect that with high probability. And other changes out in the universe are not likely to show up as test problems. And that it doesn't require a lot of manual bootstrapping, for example, provisioning the CI machine or whatever you have in your process. So there are some challenges here. And one of the challenges is everything tested, which we addressed by extending the test suite. So there's one test suite that runs on every change before things go via continuous deployment out to production. But there's also a slightly extended test suite where we test the dev tooling, for example, and we build the web pages and so forth to make sure that none of those tools break. And also run the sort of the bootstrap of actually running the test suite, i.e. what's run in the CI machine. Sort of inspired by Google, we have all of the code in a monorepo and do trunk-based development, which is a good foundation for a strong process. All of the client code are in the same monorepo. So whenever there's a change to some shared library, we test all of the data pipelines that we've written for our clients to see if any of them break. And the speed of the test suite is a challenge here to keep our productivity up. We use Spark. Spark is slow to start, so that limits the speed of our tests. And in order to gain speed, we do two things. We try to avoid doing things by reusing cached activities, and we try to do as many things in parallel as possible. And the best tool on the market for doing this is Google's build system, Bazel, which is kind of exotic to some people. It feels very comfortable to me because it came about 14 years ago, and I was in a team that was one of the early adopters in Europe at Google, and we had great success with it there. So we've decided to work with it for our smaller challenge here as well. it's specifically designed to make or to be a foundation for a strong process. So it can run builds and tests in isolated sandboxes and so forth. And it uses that strength of the process to enable a number of performance features, such as caching of test results and remote execution and shared caches and so forth. We haven't enabled all of them yet, but we can do that as the sort of tree grows. It is a bit shaky on stuff that Google doesn't use internally because those plugins are not so well maintained, or they have a bit of catching up to, I should say. So this is the choices that we made with respect to version controlling our dependencies. We have the JVM and Python dependencies are transitive, so we freeze them, we lock them down, and we check the lock files into version control. We have a bunch of dependencies that are not transitive, but also locked. And then we have some things that we are letting go a bit more loosely. For example, when we install apt packages, they are not so close to our application, so we just trust whatever is latest. We use a tool called bazel-deps, which is specific to Bazel and Scala for locking down JVM dependencies, or Scala and Java, I should say. We have specified our direct dependencies in a YAML file, and then there's a process that resolves all of the transitive dependencies, locks them down, builds this tree here on the lower right, which is Bazel definitions so that they can be expressed as dependencies to our binaries. And then it generates a file with all of the locked versions and the checksums and so forth. In this process, as we can say here, it promotes some things to higher versions than what was actually asked for in order to resolve all of the dependencies. For Python, we use something called pip tools. This is a useful package, and it's usable outside of Bazel context as well, where it does the same thing. We have requirements.in that specifies our direct dependencies. It compiles and resolves the transitive ones to requirements.txt with hashes. And we use that, and we import that into Bazel definitions, and we also read that sort of ad hoc from Python tooling and from Bash tooling, because we need these things for these definitions for the bootstrap. When we have failures, when things don't work out, these two behave differently. Python on the left, when we run the pip compile, which is the command in pip tools that does this resolving, it says that there are incompatibilities here in the versions, so I'm refusing to do this. So it breaks during the build, whereas in Java world, things are promoted silently. So if we have incompatibilities, we get no such method errors or these two weirdish errors here that come up when things are not compatible. So we need to run the test suite to detect these things. Our shipment artifacts are containers, and if you, like me, started using Docker very early, you're used to this serial Docker file that just executes one by one, executes commands. That's not how Bazel build dependencies. Bazel build the layers independently with just files, and it merges them into one image in some kind of order. How's my time here? Right, thanks. And this works well except for apt packages. There are a couple of sort of less deterministic ways to install apt packages. You can either just run a generic command, or there's this one that sort of runs the apt install commands. And I was a bit reluctant to use them because you don't get the same strong process with and predictable build and caching and parallelisms and so forth. So we did a little journey and tried to make the apt installation deterministic instead. So when you run apt-get update, you get a new file called packages.gz, which is an index of all of the latest versions of packages on Ubuntu. If we download that during the build, which is the normal thing to do when you're running Docker, it is a non-deterministic thing. You get something different every time. And that sort of breaks the Bazel model a bit. So there is a project called Distroless, which it aims to build container images that doesn't have distro at all, which is good for security. You cannot do shell injection if there's no shell to run. So we use some tooling from there and try to deterministically download the packages.gz. This had worked better if we were on Debian because they have old versions of packages.gz, so we could have controlled the updating, but it didn't really work on Ubuntu because there's only the latest to achieve or to get. So we decided to make a compromise and sort of download it before the build so that at least the build is deterministic. But this turned out it didn't work. I thought it would. It seemed to work for a while, but it gave very subtle errors by not, what we were omitting were running the apt install script that I thought I would be able to do without, but we weren't. So we abandoned this strategy. So I'm going to speak a bit about the tooling that we have in order to make the process strong. And that tooling looks a bit weird, and that's because of our business model. So bear with me for a little moment speaking about what we sell again. We have some different modes of collaboration with our clients. For the non-technical clients, we're just a black box that you dump in data on one end and you get some refined data out on the other end. For example, we have a customer where we get dumps from their databases and they get some kind of scoring what components in their process might probably fail in the next few months, so forth. With more technical clients, we work together with them, but we work in our environment all the time. But the client's code and things need to be separated. And if clients decide to work together with us, we have an option open for them to do an exit and take the factory and run it on their own after they have sort of learned the trade. And that affects how we design things to keep that option open. So we have a platform that has two distinct, different pieces. One is the base platform that the client's data pipelines cannot run without. It's in turn built on standard sort of cloud things like Kubernetes, storage, MySQL, and so forth. And then we have a part of the platform that is non-essential that we use to speed up our operational work and so forth. And I mentioned that we have encoded our processes into code. So all of the things that we do, we try not so much to document, but encode them in a command line tool similar to the sort of the G-Cloud or AWS command line tools, where all of the things they can do in the platform is represented in this tool. So there's one for the base platform, and then there's another one that we use ourselves, and this is Scling here is actually a superset of the functionality in the IAM command line tool. And with the exit scenario, the clients get only half of these and need to supply a cloud of their own instead. So in order for the process to be strong, we need to be able to bootstrap it from essentially nothing. So we have created this like a multi-phase build process that starts with a virtual machine where we place very little requirements. So it needs to be Ubuntu, it has some kind of modern Python version, and it has Docker. And from there, we can sort of bootstrap the build. So we first create a container image where we install the desired version of Python, and from that image, now we can install a bunch of our requirements as well. So we can do more smart things, so we can install the JVM and Bazel and so forth. And from there, we can install the sort of IAM command line tooling and some of the command line tools that we need in order to have sort of a full build process. So when we then run the build, it runs inside these types of container images where we have all of the tooling that we need, but we've sort of bootstrapped this so that this is fully reproducible no matter what exists on the machine here first. And in order for this to still be fast, we mount the different caches into these containers so that we share the sort of the bazel caches, the pip caches, and so forth, and also the Docker caches between them. And then we build a bot, which essentially mimics the way that a developer would try to update dependencies. It aims to be as stupid as possible or as lazy as possible and only do simple things. So it doesn't figure out, are there any new dependencies out there? It just guesses that maybe there's if I have 1.2.3 here, I'll try with 1.2.4 and see if it works. If it doesn't work, I'll get a quick 404. And it does what a developer would do. It upgrades the source and then looks in the log, what might be wrong, and so forth. Update it, checks them if necessary, and then creates a merge request if everything seems to work. This was very simple to build. It's been a pet project of mine, so I've been hacking in the evening time for a number of months. I think it sums up to a few weeks of full-time work. The bot itself is very simple. Much of the time was spent building this bootstrap chain, which is not so many lines of code, but a bit brittle and a bit odd. So that took some time, but that was actually necessary in order to just strengthen our CI process. There's a reporting dashboard, which took a while because we had this process of re-evaluating how we build dashboards in the same time, so I spent way too much time there. And there's a couple of data pipelines to sort of feed to the dashboard. The statistics one is I just made for this presentation. It's actually not necessary, but the classification one is necessary. And this is the output of the classification data pipeline. So this tells what the bot has been up to. And time goes upwards here. So at the top, there are the latest ones. And here we can see, okay, it managed to try this 351. It was a success. A merge request was created. In many cases, it tries to sort of upgrade for one after another. And this is in the middle of the differ sort of session. So it probably tried 1.9.1 first and 0.9.2 and so forth. Rule Scala is the Scala plugin to Bazel. That's one of the special cases that we have to build because we can't guess the next version. So we had to download the Git log from the Rule Scala project. They don't do releases, they only do Git commits. And then we can filter out all of the uninteresting ones to see what things that need our manual work. So this is essentially what our backlog looks like. Here we have test failures. We need to probably put down some manual work in order to make progress through dependency hell. So we tried to, for the visualizations here, I've tried to resolve the different things, right? There are a number of things that can happen. We can have not found, there is no new dependency. Great, we are up to date. We can manage to create the new dependency. It can fail in various ways, orange colors, and we can have some transient failures like out of disk space and things. Those are not so interesting. So does it work? I have a couple of graphs to show you to sort of get some insight in how it's doing. This is the number of merge requests that have actually been merged. We don't merge every single one of them, but most of them. And it spits out, I don't know, on average, 10-ish merge requests per day, so it's our most productive developer. It wasn't long ago that where people said, oh, this company, like they deploys to production daily, and we have a bot that deploys to production 10 times per day. We've been running it since like 3 months or something. It's produced 500 merge requests. These are the different sort of resolutions. And the resolution, I mean, it tries a bunch of things. And then we look at, okay, what was the final result for trying this bunch of upgrades? It tries a bunch of versions. What was the final result here? Was there any test failure? Then that it's a test failure. Or was there any success? It's a success, and so forth. So this is over time. And these are absolute numbers. This is the same graph with relative numbers. And we can see that it's kind of slightly going down. In terms of successes and more not found, so that's good. That probably means we're going to an up-to-date state. A number of things have happened here. One of the major things is that we implemented to do speculative execution. It used to be very passive and said, if there's an open merge request already, I'm not going to do anything. Now it rolls forward and saves those for later. And we've had a couple of cases where we had process flakiness, the slight difference between the CI and the Benderbot build and so forth that sort of took the process down. We can see that the different dependencies behave slightly differently, and we had some kind of outage here. There was a problem with a pip compile step. So another way to look at it is for every dependency, what was the last resolution that we saw? And that perhaps gives a better insight into whether it works or not. And we can see here up on the top that it's more and more getting not found, and the successes go down, which means that we are more and more up to date with our third-party dependencies. So that's kind of good. And the last question to ask yourself is, if a vulnerability fix comes out, how long does it take before it actually gets to us? And that can be measured with the intervals between version A, checking version A, and checking version A again. And from the 90th percentile, we're here on like about a week or so. 99th percentile, some of them have really bad luck. So there are a few of them that we don't check more often than a few weeks. So it's decent on keeping us up to date, at least. I'll skip this one. It has mostly worked well with few incidents. We had one outage caused by the bot when we upgraded to a new patch version of a component shipped by Google of all places, and it actually took down production. But we are offline batch processing, so it wasn't a super big deal. It's not open source because it's all super specific to our environment, so it wouldn't make any sense to open source it. But I'm happy to show you things if you're interested. Some resources if you want to read more on these topics. And I believe I've sort of eliminated the space for questions. Thank you.